Hello friends, welcome to my YouTube channel. So today we are going to solve GS 2026 MCQ part. Let us start. Um, so it is given that alpha be a strictly positive real number, and for all positive integers n, they are defining n to be this log of 1 plus n to the power minus alpha. So we have to check the convergence of summation n from 1 to infinity of an. Okay, so for alpha strictly greater than 0, for alpha is strictly greater than 0, we have n to the power minus alpha tends to 0 as n tends to infinity, right? And limit of log 1 plus n to the power minus alpha divided by n to the power minus alpha is 1. So this is convergent if and only if this sum converges. So we know n to the power minus alpha, when it is convergent, is convergent when alpha is strictly bigger than 1, and diverges when alpha is inside 0 and 1, right? So this is convergent for alpha is strictly greater than 1. So this is correct. So I did divergence for all, this is not correct. Convergent for 0 and 1, this is not correct. It's convergent for all alpha greater than 0 is not correct, right? So it is only convergent when alpha is strictly bigger than 1. So so this is done. Okay, now let's move on to the next question. What is the value of limit n tends to infinity product k from 1 to n, k by k plus 1 n to the power 1 by n. Okay, so let us just do it here. I hope I have space. So limit n tends to infinity product k from 1 to n, k by k plus n power 1 by n. Let us assume this is L. So this will imply log L equal to limit n tends to infinity 1 by n summation k from 1 to n log of k by k plus n. Okay, so which is nothing but limit n tends to infinity 1 by n summation k from 1 to n log of k by n divided by 1 plus k by n. Okay, so which is integral from 0 to 1 log of x by 1 plus x, right? Just Riemann integration. So this is integration 0 to 1 log of x minus log of 1 plus x dx. Okay, right? So log x, the integration term wise, by integrating term wise we have 1 plus x log 1 plus x minus 1 plus x. Okay, 0 to 1. All right, so if you put the value, you have minus 1, and if you put 0 here, this will be 0, this will be 0, minus 0, and if you put 1, you will get 2 log 2 minus 2, and minus of minus 1. Right? So finally you have minus 1 minus 2 log 2 plus 2 minus 1. So we have 2 minus 1 minus 1 cancels, so log 1 by 4. So log L equal to log 1 by 4, that will imply L equal to 1 by 4. So we have the value of the integration is 1 by 4. Yeah, the option is correct. Okay, so let us move on to the next problem. For x belongs to 0 comma 1, let fx to be the series n from 1 to infinity x power n divided by n square. So we have to check about the differentiability of that function. So let us just quickly compute the differentiation. So f prime of x equal to summation n from 1 to infinity x power n minus 1 divided by n. Okay, so you can see easily. So if you approaches x to 1 minus from the left hand side of 1, the sum, so we know this sum tends to infinity because this is a divergence and this diverges. So the point is the derivative it is diverges, the derivative diverges at 1 as we took x tends to 1 minus, but the derivative, so f prime x is when x is strictly inside 0 and 1, right? Because if x is strictly in between 0 and 1, then the series is convergent. So f is continuous but no hard differential, this is not correct. F is differentiable on 0 comma 1 and its derivative extends continuously to 0 comma 1. So this statement is correct, f is differentiable on 0 comma 1, but the point is it cannot be continuously extended to 1 because at 1 it has divergent sum. So f can be extended to a derivative function on 0 comma 1 plus epsilon. So 0 comma 1 plus epsilon, if you have 0 here, 1 plus epsilon here, so let's say 1 is here, so the derivative is not defined at 1, right? So if you approaches x to 1 minus, thus f prime of x blows up. So this is not correct, so f is differentiable on 0 comma 1, but the derivative diverges as x tends to 1 minus. So this is correct. Okay. All right. So let us move on to the next problem. So for each positive integer n and each x belongs to 0 comma 1, define the function fn of x to be sine n times exponential power minus n to the power 4 times x minus 1 by n square. Okay, so we have to check the pointwise and uniform convergence. So if so let us say x equal to 0, then fn of 0 is nothing but sine n exp minus n to the power 4 1 by n square, right, which is sine of n times exp minus n square, so which tends to 0. We know that because sine of n square tends to 0 and sine n is bounded. And if you put alpha non-zero, for alpha non-zero, it will be sine of n exp minus n to the power 4 alpha minus 1 by n squared, and this also tends to 0. Why? Because alpha minus 1 by n squared tends to alpha squared. Alpha squared is non-zero, as we assume that alpha is non-zero, and it remains bounded. And not equal to 0, and the limit is not equal to 0, then exp minus n to the power 4 alpha minus 1 by n square tends to 0. The main point is this thing, hence n square tends to minus infinity. Okay, So pointwise we know that fn tends to 0, but we have to check the uniform convergence of this guy. So if you put fn of 1 by n, then you have sine of n exp minus n to the power 4 times 0, right? So which is sine of n. Okay, and the point is, the pointwise the limit converges to 0. So if the function will be uniformly converges to 0, if the function uniformly converges to 0, then fn of 1 by n also converges to 0, right? But fn of 1 by n is sine n. This is not a convergent. It is not a convergent sequence, right? It is not a convergent sequence. Okay. Yeah, it is not a convergent sequence. So you can just prove it by this Cauchy definition. If this is uniformly convergent to some function, let's say f of x, then for all epsilon there exists a delta such that okay, it has just it here. Yeah, so for all epsilon there exists n epsilon such that for all n greater than equal to n epsilon we have this inequality, that fn of x minus f of x less than epsilon, right? So the point is yeah, fn of x minus f of x is this. Okay, so then you can conclude that this function converges pointwise to 0, right? So fx has to be so if you put x equal to alpha, if you put x equal to alpha, then you can show as fn alpha tends to 0, you have f of alpha is 0, right? So if fn of x uniformly converges to some function, the function has to be 0, right? The f of x has to be the 0 function. But the point is, then fn of x is less than epsilon. Yeah, so this is for all x belongs to 0, 1. Okay, so this is less than epsilon for all n greater than equal to n epsilon, and for all x belongs to 0, 1. Now just put x equal to 1 by n, then you will get the contradiction. Okay, because fn of 1 by n equal to sine n, which is not convergent. Okay, so this option is correct, this is not, these are not correct. Okay. Okay. Okay, let us move on to the next problem. If from 0, infinity to r be a continuous function, consider the statements: limit x tends to infinity, f of x equal to infinity, then f is not uniformly continuous. And if second one is, if f is bounded, then f is uniformly continuous. Okay, so this is certainly not true, because we know a very famous example that if you define f of x to be root x, okay, then it is clearly continuous on 0, 1, right? And we know continuous function of a closed on a closed interval is uniformly continuous. Continuous function on a closed interval is also uniformly continuous. So we know this f restriction to 0, 1 is uniform. Now we have to check what happens to 1, infinity. So The trick is that you have to find the derivative of this. So what is the derivative of this? 1 by 2 root x. Okay, so when x is greater than equal to 1, the derivative, the mod of the derivative less than equal to half, right? So then if you apply mean value theorem, this is equal to some f prime of c times x minus y, and so when x comma y greater than equal to 1, and we can find a c is inside y and x maybe, then because we let x and y greater than equal to 1, then f prime of c is less than equal to half of x minus y. So mod of fx minus fy is less than equal to half of x minus 1. Then you can just this will imply f is uniform on 1 comma infinity. Okay, so root x is uniform on 0 comma 1 and 1 comma infinity. So if you combine this together, so f is equal to root x is uniform on 0 comma infinity. So and also root x satisfies the given condition that limit x tends to infinity, f of x is infinity, right? Because limit x tends to infinity, root x is also infinity, right? So that is not correct, because it is saying that then f is not uniformly continuous. Now if f is bounded, then f is uniformly continuous. So let us check if is bounded. I think this is also not true, because let us define function f of x equal to sine x squared. Okay, and choose xn to be root 2 pi n and yn to be root 2 pi n plus pi by 2. Then what are the values of f of xn minus f of yn? So f of xn minus f of yn is just, f of xn is just sine 2 pi n minus sine 2 pi n plus pi by 2. Okay, right? So right, so this is 0, so the mod is 0 minus 1, which is 1. So the point is this is 1, right? So but mod of xn minus yn, but mod of xn minus 1 is yn is what? So mod of xn minus yn is just root over 2 pi n plus pi by 2 plus minus root over 2 pi n, which is nothing but pi by 2 divided by just multiplying numerator and denominator by root over 2 pi n plus pi by 2 plus root over 2 pi n, okay, which tends to 0. But if this is uniformly continuous, then by the definition of uniform continuity, mod xn minus yn tends to 0 implies the mod of f of xn minus f of yn has to tends to 0. But this is not possible here, because mod of f of xn minus f of yn is 1, right? It is not true. So this is also false. So this option is correct. Okay. Right. I don't have enough space here. Okay, let us see. So consider the set A to be A belongs to M10R such that A power 10 equal to 0. Okay, so A power 10 equal to 0 immediately imply determinant of A equal to 0. Just apply determinant both sides, and we know determinant of AB equal to determinant of A times determinant of B. So determinant of A has to be 0 from here. But for finding the trace, we can just look at the embedding of A. So F is an element from M10R. So you can just look at the image of that inside Mn of C, right? So if you look at its image in Mn of C, then A power 10 equal to 0, what that it implies? So inside C, we have that the characteristic polynomial. So the characteristic polynomial of A, let's say P of x, right? It is factorized in x minus lambda i's. Okay, there should be multiple roots, 1 to 10. There should be multiple roots of this characteristic polynomial, but these lambda i's are eigenvalues. Lambda i's are eigenvalues. Okay, so if lambda is an eigenvalue, then we can find a complex vector such that complex non-zero vector v. Okay, so we can find an element on Cn, C10 maybe. We can find an element of C10 v such that AV equal to lambda times v, if lambda is an eigenvalue of A, right? Then, okay, sorry. So then lambda has to be 0, right? It is clear, because AV equal to b, just then apply A square both sides. So you have A of v equal to lambda times AV, and then just replace AV by lambda v, and you will have lambda power 10 equal to 0, because you assumed that v is non-zero, because that is the definition of eigenvalues, that you have a non-zero vector such that it is possible. So every eigenvalue is 0, so lambda is 0. So the sum of the eigenvalues, the sum of lambda is a trace of A, so which is 0. So trace is also 0, is correct. Okay. All right. I think I have some space. Okay. So let us move on to the next problem. So let x comma d be a complete metric space and U be a proper dense subset of X. And let f from U to R be a function. Consider the following two statements. If f is continuous, then it can be extended to a continuous function from G to R. X be a complete metric space is a proper dense subset of it. Function. Yeah. So one is not correct. You can prove it immediately, right? Because R is a complete metric space, which is the usual Euclidean metric, and if you take proper dense subset, which is Q is dense, and just define f to be a function from Q to R, just define it f of R equal to 1 by R minus root 2. Root 2 is irrational, that is not inside Q. So clearly this is continuous function on Q, but you cannot extend it to a continuous function on R, because root 2 is inside R, so you cannot extend the function at root 2. So this option is then it can be extended continuous function to G from X to R. This is not correct, but yeah, so x comma d be a complete metric space and is a proper dense subset. Okay, now let us assume that f from U to R, where U is dense, is uniform. So what does this uniform data gives you? That if you have a Cauchy sequence, let's say this is Cauchy. Okay, so let's say this is Cauchy inside U, then you have f of alpha n is also Cauchy in R. So every Cauchy sequence is convergent, right? So the point here is that the point here is that this option is yes. So yeah, so if this is Cauchy inside U and f of alpha n is Cauchy in R, then let us define g function from x to r such that g of alpha equal to limit n tends to infinity f of alpha n, where alpha n are inside U and alpha n tends to alpha. So why it will converge it? Because this is here we will use the uniform continuity of this function f, because alpha n tends to alpha means alpha is Cauchy, and the image f of alpha n is Cauchy, so f of alpha n is convergent, right? Yeah. So we have a sequence. We have a sequence that converges to alpha because U is given to be dense, right? U is dense. So for every element inside X, we have a sequence alpha n in U such that it converges to X. Okay, converges to alpha. So that's why the limit is well defined. And now the point is how you prove the uniqueness. So let us assume the two sequence converges to alpha n and beta n. Then how you prove the uniqueness? So f of alpha n minus f of beta n. D of alpha n comma beta n is tends to 0, right? D of alpha n comma beta n tends to 0, and this will immediately imply that this mod is also tends to 0, because by uniformity of f. Okay, so this option is correct. So this is correct. So sorry, I want to check that I solved every problem. 7, 6, 5, 4, 3, 2, 1. Okay. Yeah, so this option is correct. It's correct. We are done with 7. Okay. So I don't have much space here. So let x comma d have a metric space with the additional property that d of x comma y is less than equal to maximum of d of x comma z comma d of y comma z for all x comma y comma z belongs to x. Consider the following statements for all x comma y comma z inside x. At least two of the numbers are equal. Okay. So let us just do it here. So it is given that x comma d is any other thing is given, completeness or something. No. Okay. X comma d a metric space, and d of x comma y is less than equal to maximum of d of x comma z comma y comma z for all x y z inside x. Okay. Is this the property? Yes. Okay. So let, without loss of generality, let us define a equal to d of x comma y, b equal to d of y comma z, and c equal to d of x comma z. Okay. So let us assume a is strictly less than b, strictly less than c. No two of them are equal. Okay. So we can assume that without loss of generality, right? So now by this we have a is less than equal to maximum of this is c. Yeah, so this is c, this is b, right? So b comma c, so this is, which is correct. But if you reverse, if you put d of y comma z right? So if you put d of x comma z, which is less than equal to maximum of d of x comma y comma z, right? Just shifting. It's just shifting. Okay, so then c has to be less than equal to maximum of d of x comma y. So what is d of x comma y, which is a, and y comma z is b. But this is not true because c is greater than a and b both. This is not true. Okay, so two of them has to be equal to each other. Okay, two of the numbers has to be equal. Yeah, so this is correct. So for each positive real number r and x comma y belongs to S, x, the sets b x comma r and b y comma r are either equal or disjoint. Okay, so let us assume b x comma r intersection b y comma r is not equal to phi. There will be two possibilities: either their intersection is phi or not equal to phi, right? Is not equal to phi, so then there exists a z such that is inside the intersection of two balls. Let us choose, so we want to show that b y comma r equal to b x comma r. So let us choose z prime inside b y comma r, which will imply d of y comma z prime is strictly less than r. Okay, right? So now what is d z prime comma x, which is less than maximum of d z prime comma y comma d of y comma x. Okay, now d of x comma y, so till now we didn't use the fact z is inside that, so now we are using it. So d of x comma y is less than equal to maximum of d of x comma z comma d of y comma z. Okay, now z is inside that, so z is inside b of x comma r will imply d of x comma z is strictly less than r, and z is inside b y comma r implies d of y comma z is less than r. So d of x comma y is that, right? So this is strictly less than r, this is strictly less than r, so then we have d of x comma y is strictly less than r. So this thing is strictly less than r, and d of z prime comma y is strictly less than r by this. So we have this guy, d of z prime comma x is strictly less than r. Okay, yeah. Okay, so what does it imply? This implies that z prime is inside b of x comma r. So we picked an element from b y comma r, we showed that. So b of y comma r is inside b of x comma r. Similarly, by symmetry you can show that b of x comma r is inside b of y comma r. So they has to be equal if the intersection is non-empty. So this implies this either equal or disjoint. Yeah, this is correct. So first option is true. Yeah. Okay, now I have some space finally. Okay. Okay, so given a linear map such that t is not equal to 0 and r power n equal to range of t directs some null space of t. So we know linear transformations are basically matrices. So let us define a matrix which is 0 1 0 minus 1 0 0 0 0 0. So if you when you find the kernel and the range, so let us first compute the range of the matrix x y z. This is inside M3R. So if you compute it, you will get y, you will get minus x, and you will get 0. So the range, the range of A is R2, right? It is clear from this. It is clear from this because this is the third component is always 0. Range is R2, but if you compute the kernel, so the kernel is when y minus x z is 0 0 0. Kernel is when the image is 0, then x comma y comma z is inside the kernel. So the kernel is 0. This will implies x equal to 0, y equal to 0. So the kernel means null space. Kernel of A equal to 0 0 z. Okay. So let us write down the range. So range of RA is containing this set A B 0, where A comma B is inside R, and null space is this set 0 0 C, where C is inside R. So you can look at that the intersection between range and the null space, intersection between them is actually 0, right? 0 0. Okay. And intersection is 0, then and RA plus NA, if you compute a dimension which is dimension of their intersection plus dimension of so the dimension is dimension of RA plus dimension of NA minus dimension of intersection. So dimension of RA, the dimension of RA is 2 and dimension of NA is 1. So it is 2 plus 1, which is 3. So that will imply that R3 is RA direct sum NA. Okay. All right, now this satisfies this, but the point is they are asking that T is diagonalizable or not. So let us do this here. If A is diagonalizable, over R, then there exists some invertible matrix such that A equal to PDP inverse. Then the characteristic polynomial of A is same as the characteristic polynomial of D, right? So yeah, because determinant of A minus xi has to be determinant of PDP inverse minus xi, which is nothing but determinant of D minus xi, which is just x minus lambda over psi. So my point is that you can write this determinant as x minus lambda 1, x minus lambda 2, x minus lambda 3, linear factors. But if you compute this thing for this particular matrix, you have minus x 1 0, minus 1 minus x 0, and 0 0 minus x, which is the determinant of this guy, which is minus x times x squared plus 1. X squared plus 1, but x squared plus 1 is not factorizable over R, right? So this is not diagonalizable, so this option is not correct. So now they're putting a condition. Let us check the second statement. So t is not equal to 0 is given, then that means there exists alpha. If you look at the linear transformation, there exists alpha inside Rn such that t alpha is non-zero, right? That is the meaning of t non-zero. So now if there exists a k, if there exists k strictly greater than 0 such that t power k equal to 0, so t has to be, then k has to be greater than equal to 2, because if k equal to 1, then it contradicts this fact, t is non-zero. So that means k is greater than equal to 2, then what we have is t of t k minus 1 alpha equal to 0, right? Now look at this. As k greater than equal to 2, this t k minus 1 alpha is inside range of t, right? Because this is t of something. It is actually t of tk to k minus 2 of alpha, right? So this is inside the range, and t of this thing is 0. That means this is inside the null space of t. But it is given that Rn is direct sum of range of t plus null space of t. So range of t and null space of t has only intersection at 0. So then we have t of k minus 1 alpha is 0. Okay. So continuing this argument, you will end up with t square alpha is 0. So you will have then t of t alpha is 0, and t alpha is inside the range of t, and t of t alpha is 0 implies t alpha is inside the kernel. So that will imply t alpha is 0, which is a contradiction, because we assume that t alpha is non-zero, right? So this option is correct. So A is the correct option. Okay, that means we showed that there does not exist any such k. Okay. Okay, so move on to the next problem. For any differentiable functions from R to R, G is a differentiable function from R to R. AG is a set x in 0 and 1, gx equal to 0, and bg equal to x between 0, 1, g prime of x equal to 0. Okay. Then SB the set G from R to R, D is differentiable, and AG intersection BG is phi. Then which of the following is true? So we are basically, they are asking about the cardinality of the set AG and BG. Okay, so I don't have enough space here, so let us just do it here. So G is a differentiable function from R to R, differentiable. So AG be the set x inside 0, 1 such that g of x equal to 0 and bg equal to x inside 0 comma 1 such that g prime of x equal to 0. Okay, so g is differentiable over r, right? So at every point that g prime of x is defined, they exist. So let's say AG contains infinitely many points. Okay. AG contains infinitely many points. So that means you can choose a sequence, monotone sequence Cn which is a subset of AG, because if AG contains infinitely many points, then every bounded sequence, so Cn are elements in 0 comma 1, so Cn has to be bounded, and Cn has a convergent subsequence. So I am taking, without loss of generality, let us take this is convergent, and again without loss of generality we can assume Cn is increasing. Okay, so Cn is increasing and Cn converges to alpha, and Cn is not equal to alpha. Okay, for all n. So let us just assume that. Okay, so then alpha is also inside 0 comma 1, because if Cn is convergent and Cn are inside 1 and 0, then alpha is also inside 1 and 0. Okay, now Cn is a subset of AG, so that means g of Cn equal to 0. Then limit n tends to infinity g of Cn equal to 0, that will imply g of alpha is 0. So this is by continuity. So then we have alpha is inside AG. This is observation 1. And as given in the question that G from R to R is differentiable, then what we have is that G prime of alpha exists. Okay, now if we take any sequence tends to alpha, you can compute G prime of alpha by given by G of Cn minus G alpha divided by Cn minus alpha. If you compute this limit, you have you can get the value of G prime of alpha, right? Okay, so then as we assume that Cn is not equal to alpha, this fraction is well defined, but note that Cn are inside AG, and we showed earlier that alpha is inside AG. That means this is 0 and this is 0, so this is limit of 0. So this is 0. So what we have is that G prime of alpha is also 0. That will imply alpha is inside BG. So AG equal to infinity implies AG intersection BG is non-empty. Okay, so but S is a set such that AG intersection BG is phi, that will imply AG is finite, has to be finite. Okay, so AG is finite. This is the right option. So there exists both are infinite is not true. This is not true. So this is also not true, but one can show explicitly by an example that for all G, the set BG is finite. But I can produce a function such that, yeah, this is infinite. So you don't need to check that, but okay. But let us define a function. So G from R to R, let us define a function Gx defined by x by 2 plus x square sine 1 by x when x is not equal to 0 and 0 when x equal to 0. Okay. So you can see that yeah, so you can see that this function is continuous, because as x tends to 0, this tends to 0. This function is continuous. So let us check this function is differentiable or not. So gx, so when x not equal to 0, this function is clearly differentiable. Then let us check differentiability at 0. So x minus 0, limit x tends to 0 plus, which is nothing but limit x tends to 0 plus g of x is x by 2 plus x square sine 1 by x by x. So the limit is half, and if you similarly take limit x tends to 0 minus of this fraction is again half. Okay. So now the point is this function is differentiable at 0. Okay. This function is differentiable at 0. So differentiable at 0, and it is differentiable at our non-zero point. So this function is differentiable. Okay. Now let us just compute g prime of x for non-zero x. So by the definition, it is half plus 2x sine 1 by x minus cos 1 by x. Okay. So this is the g prime of x, right, for x not equal to 0 and equal to half when x equal to 0. Okay. So don't worry about that. As x tends to 0, g prime of x has to be tends to z prime of 0. That this is not needed, because we don't know that derivative function of a differentiable function has to be continuous. It is not needed, right? So so g prime of, yeah, so derivative exists. Now okay, now we want to look at so what is the problem? Let us see again. So AG intersection BG is 5. Okay, so we will first show that AG intersection BG is empty. So let us say x by 2 plus x square sine 1 by x. Let's say this is equal to 0. So see that g0 is not equal to g prime of 0. So this is the main case. G0 is not equal to g prime of 0. But the point is that this is equal to 0 implies let's say intersection BG is not equal to phi, then if x is inside that, x is non-zero because g0 is not equal to g prime of 0. So that means x by 2 equal to minus x square sine 1 by x, which we'll have, so minus 2x sine 1 by x. Okay, so let us again assume that g prime of x equal to 0 for the same x. That will imply the half, because x is non-zero here, right? Half plus minus 1, because 2x sine x is minus 1, minus cos 1 by x is 0, which will imply cos 1 by x equal to minus 1 by 2. So from that you can say cos square 1 by x is 1 by 4. Okay, and sine square 1 by x equal to 1 by 4x square by this equation. So just add them, you will get 1 equal to 1 by 4, 1 plus 1 by x square, right? 1 plus 1 by x square, then 1 by 1 plus x square equal to 4. So then you have 1 by x square is 3, then that will imply x equal to 1 by root 3. Okay, x equal to plus minus 1 by root 3, but as x is inside 0 comma 1, we are choosing x being positive. So as x is inside 0 comma 1, if there is a solution, x has to be plus 1 by root 3. So what is the condition then? That means cos, so by this thing, cos root 3 has to be minus half. So that is not possible. So that means AG intersection BG is empty. Okay, now we have to check the zeros of the function, zeros of g prime of x, right? So g prime of x is half plus 2x sine 1 by x minus cos 1 by x. Okay. Okay. Now clearly this function is continuous on open interval 0 comma 1, because it is continuous on open 0 and closed 1. So now put x equal to 1 by 2n pi, and so put x equal to 1 by 2n pi, then g prime of x, let's say xn is this, g prime of xn is half plus, so 1 by x would be 2n pi, so sine 2n pi is 0 minus cos 2n pi, right? So we know cos 2n pi is 1, so half minus 1, so which is minus half. And if you put yn to be 1 by 2n pi plus pi by 2, then yn equal to half plus 2 by 2n pi plus pi by 2, 1, because sine 2n pi plus pi by 2 is 1 minus cosine of 2n pi plus pi by 2, which is 0. So that means this is half plus 2 by 2n pi plus pi by 2, which is positive. Okay. So that means in between 2n pi plus pi by 2 and 1 by 2n pi, this thing between this thing at this point the function has positive value, and that it has negative value. Okay, so what that implies is that there exists a root inside 1 by 2 n pi plus pi by 2 comma 1 by 2 n pi. So you can just easily vary n to get infinitely many solutions of g prime of x, infinitely many zeros of g prime of x. So our first option is not correct. Okay, all right, so yeah, okay, so let us do the next problem. This is done. So let g be a function from 1 comma infinity to r be a function such that g1 of 1 equal to 1 and g prime of x equal to 1 by x square plus g square x for x greater than equal to 1. Okay, so okay, so we have to find the limit maybe. So let us do it here. I have some space. So g prime of x is equal to 1 by x square plus g square of x. Okay, so from that we have first observation is that is g prime of x strictly greater than 0 when x is greater than equal to 1. This is the first observation. And second observation is that g prime of x is less than equal to 1 by x square, because x square plus g square x is x square plus g square x is greater than equal to x square. So just taking the reciprocal, you have g prime of x is less than equal to 1 by x square. Okay, now from that you have that g prime of x, if you take the integration from 1 to y dy is less than equal to 1 by x square integration 1 to y dy, which will give you gy minus g1, and g1 is 1, it is given in the question, which is 1 minus 1 by y. Okay, so which will give you gy is less than equal to 2 minus 1 by y, because g1 is 1. So 2 minus 1 by y is less than equal to 2, right, when y is greater than equal to 1. Okay, so this is the observation. And as I told you that that g prime of x is strictly positive, so that means g is strictly increasing function. So you can write here g is strictly increasing. So as g is strictly increasing and gy is less than equal to 2, that means gy is bounded. Gy is less than equal to 2, right? So it's strictly increasing and gy bounded, and g is continuous. Okay, then we have a limit. The limit exists. Why the limit exists? So yeah, so if you want I can prove it. So let us assume that so g is a function from 1 comma infinity to r. Okay, g1 is 1, so, and g prime of x is strictly greater than 0, and g1 is 1 that I wrote before. G1 is 1 and g is bounded. So why then the limit exists? So let us assume S to be the set g of x for x greater than equal to 1. Okay, this set is bounded. Set is bounded. So bounded means supremum of S exists. And note that is greater than equal to 0 for all x greater than equal to 1, because g1 is 1, right, and g prime of x strictly bigger than 0. So every for all y greater than strictly greater than 1, we have gy is strictly greater than g1. Okay, all right. So supremum exists. Let's say supremum of S equal to L. So that means so we will show that limit x tends to positive infinity g of x equal to L. This is our claim. I will show that. So let us choose an epsilon. epsilon be positive. So by the definition of supremum, you have for L minus epsilon, there exists y belongs to S, sorry, there exists an element from S, there exists an element from S, let's say gy. So it is such that gy is strictly bigger than L minus epsilon. Okay, this is the by definition of supremum. Okay, now then take so this y is actually depend on the epsilon, so you can just write it as y epsilon. Okay, so then take an arbitrary x which is strictly bigger than y of epsilon. Then as g is strictly increasing, g of x is actually bigger than y of epsilon. Okay, which is actually bigger than by this, which is actually bigger than L minus epsilon. Okay, so from that inequality we have L minus g of x is less than epsilon. So L is a supremum, L has to be bigger than gx, so this is positive and this is less than epsilon. So that means we have for all epsilon greater than 0, there exists a y epsilon greater than 1, precisely greater than 1, such that for all x bigger than y epsilon, we have L minus g of x is less than epsilon. So what that means? That means limit s tends to infinity plus g of x is L. So the limit exists, but we showed before that g of x has to be less than equal to 2. So that implies the limit L has to be less than equal to 2. Okay, so the limit exists and belongs to minus infinity comma 2. Okay, okay, this is the right option, B is the right option. Okay, I don't have any space here. Okay, so problem number 12, let a comma b be linear endomorphism of finite dimensional vector space over a field. Consider the following statements: every eigenvalue of AB is an eigenvalue of BA, every eigenvector of AB is an eigenvector of BA. Okay, all right, so let us just do it here. So AB, let's say lambda is an eigenvector, lambda is eigenvalue of AB. So that will imply AB V equal to lambda V for some non-zero V. But we will do this by dividing into these two cases. Lambda is 0, lambda is not equal to 0. So if lambda equal to 0, that means AB V equal to 0. There exists a non-zero vector, so that AB V equal to 0. So lambda equal to 0 means lambda is an eigenvalue. So 0 is an eigenvalue of AB. So then determinant of AB has to be 0, right? It's clear? So determinant of AB equal to 0 implies determinant of BA is also 0. So determinant of BA is 0 implies 0 is an eigenvalue for BA. So if 0 is an eigenvalue of AB, then 0 is an eigenvalue of BA. Now do it for lambda is not equal to 0. So if lambda is not equal to 0, then there exists a non-zero vector such that ABB equal to lambda V. Okay. So now multiply both sides by B. You will get BA BV equal to lambda BV. Okay. Now if BV is non-zero, then we are done. Now if BV, let's say BV equal to 0, then what we have? So if BV equal to 0, then by this equation we have A times BV equal to lambda V, and BV equal to 0, that means 0 equal to lambda V. Okay, and 0 equal to lambda V implies lambda equal to 0. Why? Because we for being an eigenvalue, this V has to be non-zero. So B is non-zero implies lambda equal to 0. So but we chose that lambda is not equal to 0, so that means BV is non-zero. BV is not equal to 0. So lambda is an eigenvector of AB implies lambda is an eigenvector of BA. Sorry, eigenvalue of AB implies eigenvalue of BA. So now let us do the next part, the eigenvector part. This is not true in general. So let's say A equal to 1 1 0 0 and B equal to 0 1 1 0. Then let us compute AB, which is, what is AB? 1 1 0 0 0 1 1 0, which is equal to 1 1 0 0, and BA is what? BA is 0 1 1 0 1 1 0 0 equal to 0 0 1 1. Okay, so now let us choose 1 1 0 0, which is AB, times 1 0. Okay, what is that? That is 1 0. So 0 comma 1 is the eigenvector for AB. But if you choose BA, 0 0 1 1, which is 0 0 1 1 times 1 0 is 0 comma 1. So 0 comma 1 is not an eigenvector of this. Is not eigenvector. Not an eigenvector. Okay. So that implies option 2 is incorrect. So this is not true, this is true. So I is true and 2 is false. Okay, we are done with 12. Okay, okay, so let us move on to the next problem, problem number 13. So let a real number A, and this is the greatest integer function. We define the fractional part of A to be that n greater than equal to 4, be an integer, then the expression. Okay. So fractional part is the lowest integer, right? So fractional part means if you have x here, n and n plus 1, then the floor of x has to be n, right? So this is the meaning of this floor function. Okay, so you have to compute this. So let us compute that. So E, we can write E. So I don't think we have enough space here. So let us do it here. So E has an expression. So this is 1 plus 1 by 1 factorial plus 1 by 2 factorial dot 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 1 by n factorial plus 1 by n plus 1 factorial and so on. Then n factorial times C is n factorial plus n factorial by 1 factorial plus n factorial by 2 factorial dot 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 1 plus n factorial by n plus 1 factorial plus n factorial by n plus 2 factorial and so on. So so it is nothing but n factorial plus n by 1 factorial plus n factorial by 2 factorial dot 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 1 plus 1 by n plus 1 plus 1 by n plus 1 times n plus 2 plus 1 by n plus 1 times n plus 2 times n plus 3 and so on. So now observe that this is an integer. This is an integer. Let us define this is m. So m plus, let us define s. This is s. Okay, m plus s. So from that we are not sure that fractional part, sorry, we are not sure that the greatest integer part from greatest integer of n factorial times c is m. We are not sure about that, not sure, because this s can contribute some integer part. So let us study s now. So 1 by n plus 1 plus 1 by n plus 1 times n plus 2 plus 1 by n plus 1 times n plus 2 plus n plus 3 and so on. So this is less than or equal to 1 by n plus 1 plus 1 by n plus 1 squared plus 1 by n plus 1 cubed and so on. Okay, right. So this is a geometric series. The value of this is as 1 minus this is this, right? So this is 1 by n precisely, and s is strictly bigger than 1 by n plus 1, right? So then 1 by s is inside n plus 1 and n. Okay. So the observation is that s is inside 1 by n and n plus 1. So s is strictly less than 1, right? S is strictly less than 1. So that means that n factorial times c is m plus s, where s is strictly less than 1, strictly less than 1. So that means the integer part of n factorial e is m, and the fractional part of n factorial e is just s. Okay, now 1 by n factorial times c fractional part is 1 by s, and 1 by s is inside n and n plus 1. So then what is the greatest integer of that? Is n precisely. So yeah, this is n. This is the right option. Okay, let us move on to the next problem. Consider the space x equal to a belongs to m to r such that a times a transpose equal to 2 minus 2 minus 2 3. Then we have to find the number of connected components of x. Okay, so we know that for any matrix A, so we will use polar decomposition of a matrix, right? We will use the polar decomposition of a matrix. So we can write A as product of, sorry, let's say we can write A transpose as a product of U times P, where U is unitary and P is non-negative. Okay, non-negative positive definite symmetric. So this is symmetric in this case. Okay, in the real case P is symmetric. Okay, so P is unitary and P is U is unitary, means in real case this satisfies U times U transpose equal to U times U transpose times U equal to U times U transpose equal to identity. This is the polar decomposition. Okay, this is symmetric, means P equal to P transpose. So you can look at polar decomposition of a matrix. Okay, so then A equal to P transpose times U transpose. That means P times U transpose actually. So now so here, so by the given condition, let us define it as M. By the given condition, A times A transpose, so A is that, and A transpose is U P transpose equal to M. So that will imply that this U transpose times U equal to I. So you have and P equal to P transpose because P is symmetric. So P square equal to M. That is a very important condition, and M is invertible. You can say, you can see that. So P square is M. This is a condition. Okay. So now we know O2, the set O2 is O2 has two connected components. Okay, O2 has two connected components. So O2 has two connected components. The O2 consisting the functions which satisfies A times A transpose equal to A transpose times all matrices, such that A times A transpose equal to A transpose times A equal to what? Identity. Okay. Now you can just define for all element inside X, you can find a P. This P is universal, right? So then you can define a map from X to O2 and O2 to X. Okay, so let us define X to O2 by this equation. A goes to P inverse A. Okay, then you can check that P inverse A times P inverse A transpose equal to what? Equal to P inverse A transpose P inverse transpose. So A times A transpose, A is inside X, so A is inside X, so I want to show that P inverse A is inside O2. So P inverse A times A transpose is M, and P inverse transpose is P transpose inverse. So P transpose inverse, so that means that the P transpose is P, so P inverse times M times P inverse, and M is equal to P square. So this is identity. So P inverse A lands inside O2, and then similarly from O2 to X you can define B goes to just simply PB, and let us just check. PB times PB transpose is PB B transpose P transpose, and B is inside O2, that means this is I, and P transpose equal to P square, which is M. Okay, so this is inside us. So and these are kind of X from O2. This is continuous bijection, and this is also continuous bijection. Okay, so you can find like that. So this is the homeomorphism. So X is homeomorphic to O2, and we know O2 has two connected components. So the connected components are easy to define. Defined by determinant of B is 1 and determinant of B is -1. There are two connected components of O2. Then we get that X has also two connected components. Okay, so this is the correct option. Okay, let us move on to the next problem. So V be the real vector space of all polynomials in Rx of degree less than or equal to 10. Consider the linear operator T from V to V defined by this. We have to find the trace. Okay, I don't have enough space here, but let us do it here. So I will do general case. So let us a linear operator defined by alpha x plus beta, and where the space is collection of all polynomials less than equal to degree k. Okay, collection of all polynomials of array less than degree 10. Okay, degree k. So I will do general case. So this is a basis. This is the ordered basis. So T of 1 is 1, then T of x is alpha x plus beta, then P of x squared is alpha square x square 2 alpha beta x plus beta square. T of x cube equal to alpha cube x cube, so on. So we only need the leading coefficient, because if you look at the matrix representation of this linear transformation, this matrix will be look like this. So first of all, T of 1 is 1, so 1 0 0 0 0 0. Second thing is alpha x plus beta, that is 1 times beta plus alpha x. So x is the second basis element, so this is beta alpha 0 0 0, and next one is something star and alpha square. Okay, so they end up with alpha to the power k. Then what is the trace? Trace of T will be summation I from 0 to k alpha power I, which is nothing but alpha power k plus 1 minus 1 divided by alpha minus 1. Okay, so in our case alpha is 2 and k is equal to 10, so which will imply that is 2 to the power 11 minus 1 divided by 1, which is 2048 minus 1, which is 2047. Okay, right. Oh, this is 2047. Yeah, so this is the right option. Let us move on to the next problem. So let 1 get less than equal to p, strictly less than q, integers f of x comma y equal to y power p minus x power q. Consider the vector space. Yeah, so let us quickly compute del f del x equal to what? Minus q x to the power q minus 1, and del f del y is p y to the power p minus 1, right? So now look, so note that y to the power p minus x to the power q is inside the ideal generated by x to the power q minus 1 and y to the power p minus 1. Why? Because y to the power p minus x to the power q equal to y times y to the power p minus 1 minus x times x to the power q minus 1. Okay, so now this is basically the given vector space is basically c of x comma y quotiented by x to the power q minus 1 comma y to the power p minus 1. That's enough. So this ideal is exactly equal to x to the power q minus 1 comma y to the power p minus 1. Okay, so now so in this vector space x to the power q minus 1, so yeah, in this vector space x to the power k treated as equivalent to 0 in V for k greater than equal to q minus 1, and y to the power m equivalent to 0 in V for all m greater than equal to p minus 1. Okay, so that means the basis vectors for this vector space is x to the power I, y to the power j, where I comma j okay, so I is less than equal to q minus 2 0 and j is less than equal to 0 and p minus 2. So then how many basis elements are there? So that is q minus 1 and there are p minus 1, which is pq minus p minus q plus 1. B is the correct option. Okay, so we have 4 more problems. Okay, let gamma inside R square be the graph of y equal to sin x, and let L be a line in R2 such that the number of gamma intersection L equal to n. Which of the following statement is necessarily true? N is even and n is odd. Okay, n less than equal to 10. So they want us to know that at how many point a line can intersect sine curve. Okay, so let us draw the picture of sine curve. Okay, here's a picture. So you can see that the y-axis x equal to 0 line intersect sin x at one point. Okay, origin. So that means the number of intersection can be odd. So now if you look so carefully, that if you let's say there is a point, so more particularly you can choose pi by 3. So if you if you draw the tangent about this line, the tangent line intersect the sine curve at exactly 2 points. So you can, so this phenomena is true. So you can draw a tangent over there, and over a tangent at this point. This can cut the sine curve at exactly 2 points. So intersection point can be even. Okay, but the point is, they are saying intersection point has to be less than or equal to 10. So this is certainly not true, because if you choose y equal to x by n sufficiently large, then if you look at this function f of x equal to sine x minus x by n, so we have to look at this function. So then if you put f equal to f2 pi n, which is what, sine 2 pi n is 0 minus 2 pi n divided by n, and f equal to 2 pi n plus pi by 2, which is sine 2 pi n plus pi by 2 is 1 minus 2 pi n plus pi by 2 divided by n, which is positive, right? So you will get as many zeros as you want of fx, because this is negative and this is positive. So then by intermediate value theorem, there exists a root, there exists a 0 of f of x in 2 pi n and 2 pi n plus pi by 2. Okay, so you can take n sufficiently large and increase this number. This will be remain less than 1, right? So the number of intersection point is not bounded. So the basic idea is that y equal to x by n. So that means if you take n tends to infinity, the slope, I mean this converges to y equal to 0. This converges to x-axis. So if you draw the lines, let's say this is equal to y equal to x by n. If you take n tends to infinity, the line actually converges to the x-axis, and x-axis cuts sine curve at infinitely many points. So this is the main idea. Okay, so none of the statements are true, so this is the correct option. Okay, so suppose that f from -1, 1 to r is infinitely differentiable, and f of x minus 1 minus x square is less than equal to x cube. So you have to find f of 0, f prime of, okay. So just put x equal to 0 in this equation. We have f of 0 minus 1 is less than equal to 0. So that will imply f of 0 equal to 1. Okay. Okay. Now the divide both side by x, mod of x, where mod of x is non-zero. So you have x less than equal to mod x squared. So now take and 1, what is 1? 1 is f of 0, right? So if you put now if you take x tends to 0, then f dash of 0, if you put now take x tends to 0, you have f prime of 0 minus 1 is less than equal to 0, so f prime of 0 is 1. Okay, now we have to compute f double prime of 2, right? Okay, so so f of x minus 1 minus x square is less than equal to x cube. Am I right? Yeah. So you have to compute f double prime of 2. There are several methods. You can just directly apply the Taylor series, so you can get f double prime of 2 is 0. But I want to use this particular theorem, that h tends to 0 plus f of x plus h plus f of x minus h minus 2 f of x divided by h squared equal to f double prime of x. okay, for a so this is given that infinitely differentiable. Oh, there is no need to worry about the differentiability. So let's put so f double prime of 0, if you want to compute that, f of h plus f of minus h minus 2 f of 0. So f of 0 is 1, so minus 2 divided by h squared. We have to compute that. So we can write it as f of h minus 1 divided by h squared plus f of h minus h divided by 1 divided by h squared. Now f of h minus 1 minus h squared is less than equal to h cube. Okay, we are taking h to be positive. Okay, we are taking h to be positive. So okay, just put the mod. I will use minus h also. So f of h for positive, f of h minus 1 divided by h squared minus 1 by h, just divide both side by h squared. This is mod h. Okay, now this is true for all h, for all h inside minus 1 comma 1. Okay, am I right? Minus 1 comma 1, yes, minus 1 comma 1, and h is non-zero. This is true for all h. So as h tends to 0 plus this guy, f of h minus 1 divided by h squared minus 1 by h tends to 1, because the difference between them tends to 0, because h tends to 0, that means this tends to 0. And if you put the same thing for f of minus h minus 1 divided by h squared, just put 1 by h minus 1 is less than equal to mod h. And now if you take h tends to 0 plus, then also you get that minus 1 by h squared plus 1 by h minus 1, sorry, this tends to 1. Okay, as h tends to 0. So yeah, just do it here. So just put this plus subtract 1 by h, add 1 by h. Okay, so this thing up here tends to 1, this thing up here tends to minus h plus, yeah, this thing up here tends to 1 also. So 1 plus 1 tends to 1 plus 1, which is 2. So you can directly apply, so f double prime of 0 is 2. You can directly apply the Taylor series expansion. So f of h is f0 plus h prime into h squared and so on minus x. Yeah, so this is the Taylor series expansion, and given by condition that this is 1 minus h squared equal to f double prime of 0 divided by 2 minus 1 h squared plus higher terms, higher degree. So this mod is, yeah, this mod is tending to 0. This mod is less than equal to h cube. So this mod is less than equal to h cube. This mod is less than equal to h cube. So as this mod is less than equal to h cube, this has to be 0, right? The first coefficient has to be 0. Or rather, you can say this f of h minus 1 minus h squared divided by h squared, the whole mod is less than equal to mod of h. So this fraction f of h minus 1 minus h squared divided by h squared has to be tends to 0 as h tends to 0. So then if you divided both sides by h square, you will left with f double prime 0 by 2 minus 1, which has to be 0. F double prime of 0 is 2. This is for competitive type exams. So this option is correct. So we are done with this. Okay. Consider the following two assertions about the group G. G is abelian. So G is abelian. If g is abelian, then the function from g to g goes to g square is a group homomorphism, because gh whole square equal to g square h square for abelian groups. 1 implies 2, and if phi from g to g square is a group homomorphism, that means phi of gh equal to phi of g times phi of h, which is gh whole square equal to g square h square, and gh whole square is gh equal to g square h square. So if you left multiply by g inverse, you have hgh equal to gh square, and then right multiply by h inverse, you have hg equal to gh. So 2 implies 1. Yeah, 1 implies 2 and 2 implies 1. Yeah, this is the correct option. Okay, so finally we have to solve question number 20. So suppose that fn is a function from 0, 1 to 1. 0, 1 to 0, 1 is continuous at increasing for each n. This is the increasing functions. They are increasing functions for each n. And fn of x is a sequence of real numbers which is decreasing for all x, right? Let f is a function from 0, 1 to 0, 1 be the function defined as fx equal to limit n tends to infinity fn of x. Okay, then to choose the right continuity or left continuity. So let us just think about, so see, in TIFR or this kind of questions, there are a lot of questions from sequence and series. So this is very important topic. So let us just define such function at first. So let us define fn of x is x to the power n. So this is a valid function because this is a map from 0, 1 to 0, 1, and this is increasing, right? This is increasing function because x to the power n plus 1 is, sorry, yeah, you know why it is increasing. So y to the power n is greater than x to the power n when y is greater than x. Okay, so that's why. Okay, so this is increasing. This first check, this is increasing for all n. Yeah, this is increasing for all n. The sequence is decreasing. So fix a particular x. So we have to show that this is decreasing. So this is clearly decreasing, right? Because x to the power n is greater than or equal to x to the power n plus 1, because x is less than or equal to 1. That's why this is decreasing sequence. Now let us define the pointwise limit. So fn of alpha, if you choose the limit n tends to infinity when alpha is strictly inside 0 and 1, strictly less than 1 and greater than or equal to 0, that is alpha power n limit, which is 0, and limit n tends to infinity fn of 1 is actually 1. Okay, fn of 1 is 1. So the function defined here in this case is 0 when x is greater than or equal to 0, strictly less than 1, and 1 when x equal to 1. So clearly the function is not left continuous, right? This function is not left continuous. The function fails left continuity at 1, right? So the function is not left continuous, but the function is right continuous. So it seems like option B will be true, but okay, f is continuous. This is not correct because f is not continuous in this example. Okay, f is left continuous but not necessarily right continuous. So f is not left continuous, so this option is not correct. So let us try to show that if the condition is satisfied, f is right continuous. Okay, so fx is defined to be the limit n tends to infinity fn of x. Why the limit exists? First question is why the limit exists for all x. So the point is fn of x is decreasing, right? and fn of x are bounded, and bounded monotone sequences are convergent. So this is convergent. So these are well defined values. Okay, so you have to show this is right continuous, right? Okay, so let us check. Let alpha belongs to 0, 1. Alpha belongs to 0, 1. Okay, you can neglect 1 because there is no point of checking right continuity at 1. So let xn be a sequence converges to alpha, and xn are strictly greater than alpha, I mean from right side of alpha, xn, and which is decreasing sequence. Okay, let us check. We will show that f of xn tends to f of alpha. Then we are done for showing right continuity. Okay, so let now first of all, observe that so if you look at this sequence f of xn, so first of all, so if x is less than y, then fn of x less than equal to fn of y, because fn are increasing functions. If you then take the limit fn of x less than equal to limit fn of y, this will imply f of x is less than equal to f of y. So the f function is also increasing, right? Okay, so now we have a decreasing sequence to x alpha. So xn is greater than actually xn plus 1. That will imply f of xn is greater than or equal to f of xn plus 1, right? So f of xn is decreasing sequence, and by definition of f of x, this is the limit of fn of x, and fn of x are inside 0 and 1. So as f of x exists, and f of x is inside 0 and 1 also, right? So f of xn are bounded, and this is decreasing sequence, so this is convergent, right? Decreasing and bounded, this is convergent. Okay, convergence. Let's say limit n tends to infinity f of xn is L. So now let us check one thing. So f of alpha is limit n tends to infinity fn of alpha, right? Now we know that alpha is less than xn, right? Alpha is less than xn. So you have so alpha is less than xn. So claim is that L is greater than equal to f alpha. How you can show that L is greater than equal to? So how we show that L is greater than equal to f alpha? So let's say so so f of xn is greater than equal to f of alpha. That is true. f of xn is less than equal to f alpha, that is true. Okay, because xn strictly greater than alpha. If as xn strictly greater than alpha, we have f of xn greater than equal to f of alpha, right? So as we proved before, this is decreasing sequence and this is convergent, this is converges to L, and we proved before that x less than is strictly less than y implies fn of x is less than equal to fn of y. Then taking the limit, we showed that f of x less than equal to f of y. Now as xn less than alpha, we have f of xn greater than equal to f of alpha, right? And then taking the limit, we have is less than greater than equal to f of alpha. So L greater than equal to f of alpha. Our claim is that if L equal to f of alpha. So let's say L is strictly bigger than f of alpha, let's say. Okay. Now choose any epsilon greater than 0. Okay. Then by definition of f of alpha, we have if n epsilon of alpha is strictly less than f of alpha plus epsilon. So we have to notice one thing, that f of x is greater than or equal to fn of alpha, fn of x for all x. Why? Sorry. Yeah, you have to notice one thing, that if n of alpha is greater than or equal to f alpha for all alpha. Why? Because if n of alpha is greater than equal to fn plus k of alpha, because this fn of x is a decreasing sequence for all x. So fn of alpha is greater than equal to fn plus k alpha, and now taking k tends to infinity, you have fn of alpha is greater than equal to f alpha. Okay, this is the point. So this is less than f alpha. So choose any epsilon. So for this epsilon, there exists n epsilon greater than 0, belongs to natural number, such that this is less than f of alpha plus epsilon. Okay. Now now we choose a sequence xn, decreasing sequence, that converges to alpha, right? This converges to alpha, there is no doubt about that, converges to alpha. So then we have f of n epsilon of this sequence converges to f of n epsilon of alpha, because f n alpha are continuous, right? And in as xn is greater than alpha, because we are approaching right from right side, so f n epsilon of xn is greater than equal to f n epsilon of alpha. Okay, so that means it converges to alpha. That means for epsilon greater than 0, there exists a k epsilon, such that if n epsilon of xm is less than if n epsilon of alpha plus epsilon, right? For all m greater than equal to k epsilon, right? This is there is no doubt about that, right? There is no doubt about that. Now what we have is that, so yeah, this is greater than equal to, yeah, so this is true. Now what we have is that if n epsilon of xm is less than, combining these two, is less than f of alpha plus 2 epsilon for all m greater than equal to k epsilon. Okay, till now it is okay. Okay, okay. Now note one thing that I wrote down before, that fn of alpha, if for any alpha fn of alpha is greater than equal to f alpha, right? We want to use that. So if n epsilon, this is for all n, so if n epsilon of xm is greater than equal to f of xm, right, for all m, so what do we have? F of xm is less than f of alpha plus 2 epsilon for all m, which will imply, taking the limit m tends to infinity, f of xm is less than equal to f of alpha plus 2 alpha. We can take m tends to infinity because m is greater than equal to k epsilon, which is imply L is less than equal to f of alpha plus 2 epsilon, which imply f minus L minus f of alpha less than equal to 2 epsilon. But we assumed L minus f of alpha is strictly greater than 0. This is not possible, because this argument is true for all epsilon, so this is not possible. So L has to be f of alpha. So what we have? Yeah, L equal to epsilon, f alpha, L equal to f alpha, so it is right continuous. So f is right continuous, but we produce an example which is failed to be left continuous. So this option is correct and this is wrong. This is done. Okay, thanks for watching. So we will do the true false case part B in our next video. Okay, thank you.